Hello everybody, this is the second in a series of 3 videos about the natural logarithm and the exponential function. What makes a logarithm a logarithm? So what is its characteristic property? Well, it transforms products into sums. Remember that ln x was defined as an area. If we can show that this area over the interval between 1 and a is the same as this area over the interval from b to ab, then we are done. Because the area to the right is a difference of ln of a times b minus ln b. Then we only have to add ln b on both sides and we are done. So let's show that these two areas are equal. Actually, we only need to show that for any Riemann sum on the left, there's a Riemann sum on the right, which has the same area. Because if this holds for all Riemann sums, we just approximate the area to the left by better and better Riemann sums, and the equality must hold in the limit as well. The statement for Riemann sums boils down to understanding why for any single rectangle on the left, for instance, the second one, the corresponding rectangle on the right has the same area. Here it helps to think of the numbers 1, a, b, and a times b in a more geometric fashion. The number 1 corresponds to the line segment O1. To get a point representing b on the x-axis, you stretch this line by a factor b. Likewise, you get the point representing ab by stretching a by the same factor b. Now, we cut the left interval into n subintervals. In the picture, this would be 4. The left and right ends of these subintervals will be numbers x0, this is 1, x1, x2, x3, and x4, this is a. The area of any of these rectangles on the left will be width times height. Let's focus on the second rectangle. Its right end is x2, its left end x1, so this difference, x2 minus x1, is its width. For the height, you just plug the right end x2 into the hyperbola function y equals 1 over x. Never mind that we used the midpoint of the intervals when we defined the Riemann sums some time ago. We did this because it's better for numerical calculations. Here it's more convenient to use the right end. The corresponding points on the right we get by stretching by the factor b. x0 equals 1 stretched by b gives b, as we've seen. x1 stretched by b gives x1 times b, and so on. So in general, the cutting points in the right interval will be xk times b. Then their width will be this difference, and their height this fraction. Now we simply factor out b from the difference, cancel with b in the denominator, and then we see that both rectangles have the same area. So our proof is done. Our next goal is to define the exponential function, the one with base e, the Euler number, y equals e to the x. One might call it the natural exponential function, like the natural logarithm, but in fact it's so natural that people even drop the natural and just call it the exponential function. A quick reminder, what is a function? A function is a rule. If you have an input x, this rule tells you that what the output y will be. Symbolically, we write this sometimes like this. F, the name of the function, takes an input x and assigns it to the output y. We also need to tell people which is the domain of the function, which inputs are allowed. An example would be the square function, which simply squares a number x. You will see in a minute why I want the domain to be only the non-negative numbers. If we plot all the points, we get the graph of f here. This is half of a parabola. With a graph in front of you, you may throw away the rule which you used to plot it. The graph allows you to define the same function by a geometric rule. Take a value x on the x-axis as an input, go upward until you hit the graph, go to the left until you hit the y-axis, this is your output. Another reminder, what is an inverse function? If you look at the last picture, you may wonder why this geometric rule started on the x-axis. We may as well start on the y-axis, and this gives us the inverse function. We define the inverse function by means of the graph of the original function. Start with an input x, which is now on the y-axis, but I call it x nevertheless. Go to the right until you hit the graph, go down to the x-axis. This defines the root function, which is the inverse function of the square function. If you apply these two functions one after the other, so you start with a blue x, go to y, square root of x, then you apply the square function, which backtraces you to the input x, then you get the original definition of the square root. Remember, the square root of a number, x, is a non-negative number, which, if you square it, gives you back x. If you start with the red x and do the same, you will get this second well-known formula. In a way, when defining the inverse function, we simply flip the roles of the x-coordinates and the y-coordinates. In order to get the usual graph of the inverse function, we only need to flip the x-axis and the y-axis about the angle bisector. This is the dashed line here. After all these reminders, we can finally define the exponential function. It is the inverse function of the natural logarithm. So you start with an x on the y-axis as an input, go to the graph, go down to the x-axis, and your input is the exponential function of x. As with the square and square root function, we get two important formulas. They are crucial for computations. Start with x. First apply ln, then apply x. You will get back x. Why? So start here, go to ln x, apply x with x, you'll end up here. So the second formula can be seen similarly. As before, the graph of the exponential function is just the graph of ln reflected about the dashed angle bisector y equals x. The exponential function is the opposite of the natural logarithm, so its characteristic property will be the opposite as well. It transforms sums into products. Let's start with two numbers, capital A and capital B, on the y-axis. We go to the right until we hit the graph. We always hit the graph eventually because the range of ln are all real numbers, and so we can find numbers small a and small b such that this holds. So we want to compute x with capital A plus capital B. First, we replace them by ln A and ln B. We've just seen why we can do this. Then we apply the characteristic property of the natural logarithm. Next, we apply one of those formulas which we've seen a few seconds ago. And finally, we replace small a by x with capital A and small b by x with capital B. This finishes the proof. We will see in a minute how we can apply this characteristic property. But first, let's define the Euler number. It is exp of 1. So start with 1, go to the graph, you end up with e. Or you may say it is a number e such that ln of e is 1. Remember the definition of the natural logarithm as area? Start at 1. Imagine that if you go to the right, an area appears like a opening, no, closing curtain in a theater. While you're closing this curtain, keep track of the area which appears and stop exactly when this area is 1. This number where you stopped is the Euler number. Finally, we need to show that this new function, x of x, is nothing else but the exponential function e to the x you already computed with for quite a while. I mean, it's not clear at all that they are the same. The function exp is the inverse of a function which we defined as all the areas under a hyperbola. The other function is just the powers of a certain number. Why on earth should these two be the same? I find it quite charming that you can pull the proof out of a hat like a magician pulling out a rabbit. And the hat here is the characteristic property of x of x. That said, I will not provide the full proof, but only 3 examples which should convince you that these two functions are indeed the same. The first example, we take a natural number, say x equals 2, and x of 2 is obviously x of 1 plus 1. We apply the characteristic property. Since x of 1 is e, we have e times e, or e squared. So x of 2 is e squared. We may use the same argument with x equals 3 and x equals 4 and with any natural number n, so we have this. As a second example, we look at a fraction, for instance x equals 1/2. By definition, e is x of 1. We can write 1 as 1/2 plus 1/2. Again, the characteristic property. Now we have e is equal to x of 1/2 squared. If we take the square root on both sides, we get what we want. In the last example, we look at a negative number, say x equals -2. First, we have 1 equals x of 0. To see why this is true, either stop here and look at the graph of exp, or write down ln of 1 is 0 and apply exp on both sides. Now, 0 is 2 minus 2. Again, the characteristic property, and exp of 2 is e squared. Now we have 1 equals this. Divide both sides by e squared, and we get what we want. I'll leave it as an exercise, it should be fun, to show that fractions like 3/2 work as well. To show that it works for irrational numbers as well involves limits. After all, every irrational number is a limit and of rational numbers, and you only need to show that x behaves well with limits, that it is continuous, but I will not do this here. In the next video, I'll explain why the derivatives of ln of x and e to the x are what they are.